All right, so we're going to be talking some more about series, sequences and series. Hopefully by now you have a good working definition of what I mean when I say a series, what I mean when I say sequence, and the types of questions that we are going to start to ask are questions like, does the series converge or diverge? Now remember, a series is the sum of a sequence, right? So you have a set of numbers that we have, that is a sequence, and we were asking, what's the sum of that sequence? Would be a series, right? So we have a finite series, infinite series, but again, it's a question of convergence or divergence. So the idea of does the series converge or diverge, meaning if you were to continue to list out uh, the terms of the series, will it converge upon a number or diverge as n goes to, let's say, infinity, because we're interested in the um, in the infinite series, infinite sequences. And then the next question is, well, wait, if it does converge, then what is its sum? What does it add up to be? That previous example, previous video, we saw that 0.3333 forever could be thought of as an infinite sum. And then we wanted to know more than just does it converge. We actually wanted to know, if it does converge, what does it converge to? All right, and we saw that how you can write 0.3333 forever as 1/3. Now, what I'm going to do is I'm going to be using some of the language that you see here for an infinite series, and I'm going to put them to use on the next page. So I'm not going to spend a lot of time with this language here, because you're going to see all of it on the next page. Okay. So let's start. So here we have a series, and notice the notation that we're using. And in this case, we are, it's an infinite sum from, right, 1 all the way to infinity. And the nth term, the general term that we're using here, is 1 over 2n. Now, for the first few of these, what I want to do is actually want to go through and start back with sequence, and then start to build up with build our vocabulary. Okay, so just remember that a sub n is what we call the nth term. All right, so let's start right now. We're going to list the first 5 terms of the sequence. We're not worried about the series yet. So 1 over 2 to the power of n, that is our nth term. So if you wanted to know what the first term was in that sequence, you would plug 1 in for n. 1 over 2 to the power of n is 1/2. So that's the very first term in the sequence. Now you plug a 2 in for n, and you would get 1/4. That's the second term of the sequence. Then 1/8, 1/16, and 1 over 32. Now I'm going to stop here because I just wanted to list the first 5 terms. And now let's start to think about what we call the partial sums. All right, now if this does, if you can actually add up all of these partial sums, and it does actually add up to a finite number, then that is what we call S, or the sum of the series. That's what it adds up to be. Now, S sub n, just like A sub n, is the nth partial sum. Okay, now, in other words, what I'm saying is, look, you agree with me, I stopped after 5 terms. Now, if all I cared about were the first 5 terms, then I might ask, what is S sub 5? That would be, what is the sum of the first 5 terms of the sequence? Now, if all I cared about were the first 2 terms, then I might ask, what is S sub 2? Because that's the sum of the first 2 terms. But if I want the entirety of the sum of the series, all right, so then you'll start to see how we approach that. So what I'm going to do right now is I'm going to list the first 5 partial sums. Now, partial sums, because we haven't added up all of the terms of the sequence, but we're going to start to see what the partial sums look like along the way. So let's see if you can follow me here. So S sub 1, well, there's nothing to add up because you start with a half and there's nothing to add to it yet. Now, S sub 2, that would be asking, what is the partial sum of the first 2 terms of the sequence? Well, the first term is a half, the second term is a fourth. So the sum would be, we got a half and a fourth, so we got 3/4. Do you understand that the sum of the first 2 terms of the sequence, so here's the first 2 terms of the sequence, the sum of the first 2 terms is 3/4. Now, I'm going to keep going. S sub 3 would be 1/2 plus 1/4 plus 1/8. I think you're starting to see the pattern here. So in that case, a half plus a fourth plus an eighth is 7/8. Now, I want you to notice some things. We don't have enough tools yet to start making any declarations, but I want you to notice that you started with 50 cents, and the very first sum, the very first plus button that you used, was to add a quarter, right? 25 cents to your 50 cents. But then you started, your next time you did an addition, notice that what you're adding is smaller than what you added in the previous term. Okay, so we'll see if that actually, what that possibly could mean for us in just a little bit, but I'm going to go ahead and give you S sub 4 would be 15 over 16. That's if you added up a half plus a fourth plus an eighth plus a 16th. And S sub 5 would be 31 over 32. Now, if you ever see any silly arithmetic mistakes, just bear with me. But that is going to be your first 5 partial sums. Now, where are we going here? So what I want is the nth partial sum. I have an A sub n. That's how I tell which term comes next. But I want an S sub n. And what would that give us, right? So if I could form an nth partial sum, that would be really nice, because now, instead of doing what I'm doing off to the side here, I could just plug, say, 2 into this nth partial sum, and I would get back out 3/4. Or I would plug in a 5 here, and I would get back out 31 over 32. In fact, I could keep going no matter how far I want to go out. And then eventually, I'm going to want to take the limit of that. I hope that makes sense, because right now I don't have anything to take the limit of as n goes to infinity. I need to form. All right, and now stay with me. This is not an easy chapter, and this is not easy material. So how do I get an nth partial sum? Well, you're going to have to be able to look at each partial sum and see if you can spot the pattern to be able to build the nth partial sum. It's not given to you. You have to use the partial sums to get there. So what I'm going to do is I'm going to just list out so that you can see them side by side. I'm going to go ahead and list out the first 5 partial sums. So a half, 3/4, 7/8, 15 over 16, and 31 over 32. Now, let's see if I can just use those partial sums to find a pattern. All right, so what are we doing? Well, we're looking for a pattern. Let's start with the denominator. Now, 2, 4, 8, 16, 32. Now, that is fairly easy to model, right? That's 2 to the power of 1, 2 to the power of 2, 2 to the power of 3. So I know that I can represent the denominator of that nth partial sum as just 2 to the power of n. Now let's look at the numerator. Now it goes from a 1 to a 3 to a 7 to a 15 to 31. And the question is, can you find the pattern such that you can write the numerator as a function of n? And how do we do that? Well, notice that the first numerator, right? Notice that 1 is one less than 2, the denominator. 3 is 1 less than 4. 7 is 1 less than 8. 15 is 1 less than 16. Do you see how it's always minus 1? Right? So it would be what minus 1? Well, if it's always 1 less than the denominator, well, the denominator is 2 to the power of n. So but it's got to be 1 less than that. The numerator is always 1 less than the denominator. So minus 1, 2 to the n minus 1. All right, now this takes a little bit of practice. You could always experiment a little bit more if you wanted to experiment, but let's assume that you can get S sub n, the nth partial sum. Then the idea is, okay, well, the nth partial sum is great because it can tell me the sum, and all I have to do is give it a term, which term of the sequence I'm at. But since we are looking for the sum of the entire series, right? We're looking for the sum from 1 to infinity. Then we're going to go back to the idea of using the limit, and we're going to take the limit as n goes to infinity. So in this case, we're taking the limit as n goes to infinity of 2 to the n minus 1 over 2 to the power of n. All right. Now, I'm not going to go through more of these techniques that I'm going to tell you. You would use L'Hopital's rule here. And what you would end up with is the limit as x approaches infinity. If you start to use L'Hopital's rule, you would get 2 to the n ln of 2. If you don't know how I did that derivative, you need to go back to the previous video. Over 2 to the n times ln of 2. Well, 2 to the n times ln 2 divided by itself just equals 1. Now, what did we just do? Well, hey, what if somebody were to come along and say, hey, what's a half plus a fourth plus an eighth plus a 16 plus 1 over 32? Well, even if you don't like fractions, you still could, just with a reasonable amount of time, give them an answer that the sum of those 5 numbers is 31 over 32. But what if they did not stop? What if they said, and they continued plus, and in fact they continued all the way as n approaches infinity. What you have just found is that if you would continue in that addition, although that's an infinite amount of terms, the result of that infinite amount of addition and summation is actually a finite number. These, if you keep going in your addition, it actually adds up to 1. It converges, and its sum is 1. So let's write that. So what is the takeaway? It converges, and the sum is 1. Okay, so let's do another one. Now I'm going to go through this first part a little bit faster, but you can basically see that the idea is the same. They were asked to find another sum of a series, right? So the series in this case is 1 over n minus 1 over n plus 1. All right, now what I'm doing here is I'm going to use the nth term. What is the nth term? Well, that is the a sub n. And I said 5, but I'm actually just going to do first 3. First 3 terms of the sequence. Well, here it is. If you plug in 1, you would have 1 over 1 minus 1 over 1 plus 1. If you plug in 2, if you plug in 3, and here it is. This is the first term of the sequence, second term, third term. All right, now, if you want to start to find, we're going to do, again, I wrote 5, but I'm actually only going to do the first 3. We're going to list the first 3 partial sums. Let's start with the very first sum. Well, there's nothing to add yet. It's just 1/2. Now, s sub 2 would be the first term, which is of the sequence, 1/2, plus the second term, which is 1/6. S sub 3 would be the first term, plus the second term, plus the third term. Okay, and I'm going to go ahead and box in these partial sums. So the second partial sum, well, what do you got? 1/2 plus 1/6. So that should be 4/6. Right? And if you, we can reduce that in just a second. And then if you do 1/2 plus 1/6 plus 1/12, let me just make sure. I think that should be 9/12. I'll confirm that really quickly. Yeah, so that should be 9/12, which should reduce to 3/4. Okay, so 9/12. Okay. All right, now, so yes, you can go through and reduce that to 3/4. You can go through and reduce that to 2/3. But what I'm going to do right now, since I want to use this information to help me find the general or the nth partial sum. So I'm going to go ahead and list out. I'm going to go ahead and list out the partial sums for each of these. So that would be 1/2 and 2/3 and 3/4. Okay, and again, the game is: can you use this information to represent the partial sums here, or we should say the nth a partial sum. So okay, I'm going to actually go ahead and get us there. I don't want to spend. This is one of these things that you'll have to teach people how to find patterns. We know things like 2n is the even numbers, 2n minus 1 is the odd numbers. I mean, but it's very hard to teach how to spot patterns. So in this case, here's what the nth partial sum would be. It would be 1 minus 1 over n plus 1. I'm going to go ahead and just box that in. All right, so 1 minus 1 over n plus 1. All right, so now, at this stage, what does this do for you? Well, if somebody asked you to add up the first, so we only have the first 3 terms of the sequence, but let's say you went all the way out to 10. Well, you could do a bunch of addition to get to that nth partial sum of that 10th term of S sub 10. Or you could just plug 10 into your S sub n. Right? And in other words, what if I were to plug a 1? What if I were to plug a 1 in for here? That would be 1 minus 1 over, 2. That would be 1 minus a half, or a half. So, all right. But the goal of that was such that I could take the limit. Right? So let's go ahead and take the limit of that nth partial sum. All right, and let's see if anything interesting happens. Well, I'm not going to go through. I mean, it's fairly easy to do. It's gonna end up being, as you take the limit as 1 goes to infinity, it's going to end up being 1 minus 0, or just 1. So, in other words, we get to say that this converges, and the sum is 1. All right. And again, just notice that 1/2 is larger than 1/6, and 1/6 is larger than 1/2. So every time you add, you're adding a smaller number and a smaller number and a smaller number. And we saw that it converged. Okay. So again, not enough to formalize anything yet, but this last one, now I'm going to go through this pretty quickly, because let's look at the series. We want to take the sum, right? It's the series, and what is our general term? What is our nth term? It's just 1. Right? So if you think about that, what would be, well, let's just list what's the first term, right? I mean, look at your general term. Do you see how there's nothing to plug in? There's nothing to plug in, substitute into. So a sub 1 is 1, a sub 2 is 1, a sub 3 is 1, a sub 4 is 1. Now, if you start looking at your partial sums, well, 1 plus 1 is 2, 1 plus 1 plus 1 is 3, and so forth, right? So, in this case, what do we get? Do you notice, how do we write S sub n? Well, notice how n matches. So S sub 2 is equal to 2. S sub 3 is equal to 3. S sub 4 is equal to 4. In other words, S sub n is just equal to n. And now, if you take the limit, right, with n going to infinity of n, what do you get? Well, you get infinity. So we get to say that obviously this diverges. And it doesn't have a finite sum, right? And in fact, we can make a statement that all arithmetic series diverge. Now when I say all arithmetic series diverge, there is a trivial case. So for example, like 0 plus 0 plus 0 obviously actually converges to 0. But aside from the trivial case, all arithmetic series diverge. Okay. So so let me bear with me here. So in that example, the 1b, right, on the previous page, that is a type of series that we call a telescoping series. And in the form, if you notice, it's let's do this. This type of series that we saw in example 1b, the second example, is what we call a telescoping series, and this is what a telescoping series, the form that it would take. Now, I am going to, since we're still learning, I'm going to go through this a little bit. I want to go through this a little bit faster, but notice that if you want to find the sum of the following series, you absolutely can continue to go through the steps. Let's say the first 5 terms of the sequence, then list the first 5 partial sums, and then use the partial sums to find an S sub n, and then take the limit as n goes to infinity of that nth partial sum. So what is the best way of doing this? So if you take, what I'm going to do is, if we take this a sub n, right, so a sub n, now that's given to us as 2 over 4n squared minus 1. But so that you can see what they mean by this telescoping series, you can rewrite this. Now, you would have to use partial fractions, but you can rewrite this as 1 over 2n minus 1 minus 1 over 2n plus 1. Okay, so you can use partial fractions decomposition to break up that fraction and write it as such. And now what you would find is, if I were to, I'm not going to go through and list the first terms. If you want to plug in a 1, plug in a 2. I want to jump right to when you start to think about the partial sums, right? So let's start with S sub 1. So the very first term in that, and let's see here, let me write it like this. The very first term in that sequence, I would have to plug a 1 into a sub n. So what would that look like? It would be 1 over, 2 times 1 is 2 minus 1 is 1. So it would be 1 over 1 minus 1 over 2 times 1 plus 1. So that would be 3. So 1 over 1 minus 1 over 3. That would be the first partial sum. Now, the second partial sum would be, what do we got? 2 times 2 is 4, minus 1 is 3, so this would be 1/3 minus 1/5. This would be 1/5 minus 1/7. Okay, so now you could continue in this fashion, but what would you do if you start to think about when you take the sum, right? If I were to, let's say, if I were to take, this is actually, I should not have written it there. This should actually go here. This is what happens when you run out of space. I'll show you. I'll show you exactly what I'm doing in just a second. I just wrote it in the wrong spot. So this would be 1/3 minus 1/5. And this would be 1/5 minus 1/7. Okay. So the very first S sub 1, right? That would be what I had here, 1/1 minus 1/3. But notice that S sub 2, that would be, think about it, that would be the first term plus the second term. So that would be 1/1, and I don't need to go any farther than this one to show you this pattern. Ready? So I just wanted to show you this pattern. Plus what? Plus 1/3 minus 1/5. And here is this telescoping form. Notice that if you were to drop those parentheses, right, and combine, do you see how this positive 1/3 would cancel this negative 1/3? And you would simply be left with 1 minus 1/5. And if you were to continue to play this game, you would see how this negative 1/5 would cancel this 1/5. So see how you're seeing this cancellation in this telescoping series. So what ends up happening is that the nth partial sum is always going to have 1, and then it's going to be 1 minus, and then I'll see if I can show you how you can get to this next part. So 1 minus. So I'm going to do it from here. So it would be 1, and then these 1/3 would cancel. Then it would be a 5th, and then you would have the 1/5 would cancel. Then you'd have that 1/7. So you end up going 3, 5, 7, and you can write that as that. Those are just odd numbers, 2n plus 1. All right. So I do know, I know that that's tough to build the partial sum, the nth partial sum from the partial sums. It's also tough to teach. So let's just stay with the fundamental ideas. I don't want you to get hung up. If you will allow me to, please don't get hung up on. I don't see the pattern. I don't see the pattern. Okay, so just focus on the form of how we're going from sequence to partial sums to nth partial sum to what? To the total sum of the series. Okay. So in this case, once we have S sub n, we would just simply be taking the limit with n going to infinity of S sub n. And that's pretty easy to do because as you take n approaching infinity, this is always going to zero out. And what you're going to be left with is just 1. So this converges. And the sum is 1. All right, so let's keep going here. We have discussed geometric. I'm not going to stay here very long because we've already discussed this. So remember, geometric series, as opposed to arithmetic series, you have seen me write a geometric series, and you see me discuss that R as what we call the common ratio. And you've also heard me discuss that, look, if R is between 0 and 1, then this is the way that you can represent the sum of that geometric series, right? So again, as long as R is actually the way you want to think about it is actually if R is between you, I instead of using the absolute value, let me just write it this way. So that means if you have between -1 R and +1. Okay, so that's that way you don't have to think about the absolute value of R. So if the R value, in other words, the common ratio, in other words, this this base here, if it's between -1 and +1, then you can make a statement about convergence. Okay, ready? Let me read. So a geometric series with that common well, let's say it this way: a geometric series with a common ratio R diverges when what? When the absolute value of R is greater than or equal to 1. So look, if it's past 1 or below -1, we get to make a statement that that series diverges. If R is between -1 and +1, then the series converges to the sum. So ready? Let's actually just practice that a little bit. So it's just a matter of it's not that bad. And in other words, how about this? Do you get to use this formula to find the sum of a geometric series? Because that would be beautiful, because that's look, there's no limits there. There's nothing to do there, right? It's you get to use this formula. Well, you do, assuming that the common ratio is between -1 and 1. That's the takeaway. All right, so in this case, let's look at our first example. So 3/2 to the n. So this is something you want to write down. So you can think about that, right? Because our question right now is this a geometric series? If it is, what is R? That's our real question. Well, first off, I want you to write down this because you can rewrite this as, again, I'm going to write the sum, so n is equal to 0. You can bring that 3 out front and think about it as 1/2. Now, I'll keep this as 1/2 to the n for just a second. But don't you know that if you have, let's say you have a over b to the power of n, you know that that's just a to the power of n over b to the power of n, right? We know that. But now, if in this case, if we had 1 over b to the power of n, then that would also be 1 to the power of n, which is just 1 over b to the power of n. So I want you to take that little piece of information that you already know, and I want you to think about how you could rewrite this 1/2 to the n. There had to have been an n out here that you distributed or you multiplied such that 1 to the power of n is still 1 and 2 to the power of n is 2 to the n. So we can go a little bit farther, and I don't have to do this every time, but I want you to see where this comes from. Because the idea is you want to be able to recognize a geometric series when possible. So we're actually going to think about this as 3 and then 1/2 to the power of n. So that little hopefully that explanation helped you how we go from here to here, because now we got this. This is actually very easy from here. So just let me go ahead and write, if you have a r to the power of n. In this case, we have found out that r would be equal to 1/2. So we have r is equal to 1/2, and a is equal to 3. Now, to not jump right to this formula, a divided by 1 minus r. Don't jump there yet, because you have to make sure that r, the common ratio, is between -1 and +1. Well, it is for this case. So it's only at that time do you get to plug in for a, plug in for r, and then let me go ahead and write it. So this was going to end up being is going to be 3 over 1 minus 1/2, or 6. So that is the sum. We know it converges. It's met our qualifications for the theorem. We know it converges, and the sum, the series converges to the sum, and that is the sum, 6. All right, well, how could you think about, well, this is actually even easier. So what is r? Well, first off, what is a in this problem? What is r? Let's start there. So just remember it's a r to the power of n. So in this case, a would be 1, and r would be 3/2. Well, 3/2, that's $1.50. Obviously, that is not between -1 and +1. So remember, we get to say that a geometric series diverges when that's not the case. So we get to just make the statement that it diverges. Right? Why? Because r is greater than or equal to 1. The y is important. You don't, like, the majority of the questions in this chapter are binary. It converges or diverges. So you got a 50, it's like a true or false. Like you got a 50-50 shot. If you don't tell me the right why it diverges, or then I don't get to give you full credit. Okay, so the why is important. All right. So you can, on your own time, you can read through some of the properties of infinite series. This is fairly self-explanatory. This is the way you would read this, is just look, if the sum of some series equals a, of a convergent series equals a, and the sum of some other convergent series equals b, then what can we say about using CA or something like that? So the idea is that I want to go to next is a very, very, very important test, and I'm going to go ahead and pause this video, and we're going to pick up next video on this exact topic, because this is very, very, very important test, which is what we call the nth term test for divergence, and I will see you then.